Okay, so we're going to move on now to section 3.0, which is going to start covering forms of energy. A lot of the stuff we're going to talk about today is stuff that we've already had discussions about before. So it's not going to seem super new today, with the exception of one thing we're going to cover towards the end of today, and it shouldn't be too long of a lesson. So here we go. Woo, way too fast. There we go. Now, here we go. So here's today's plan. We're going to look at the various types of energy, as well as how we're going to look at various types of energy, not the various types of energy. What the heck? We're going to look at various types of energy today, as well as how electrical devices convert one form of energy into another. We've already had discussions like this several times before, but we're going to look at it again. So forms of energy, chemical energy, energy conversions, and thermocouples, which is the brand new thing. Those are going to be the focuses of today. Here we go. So forms of energy. It seems most of you already have a pretty good grasp of this, but there are a few people that I think just aren't too sure of this. Now, before we even talk about any of the forms of energy, I think we should really just take a step back and talk about what energy is in the first place. Energy is defined scientifically as the ability to do work. So in other words, the ability to perform some sort of movement or some sort of change, basically. Now, recall that energy can take many different forms. On this picture right here, you can see that it breaks it down into kinetic energies and potential energies. Kinetic energies they define as being things like thermal energy. Thermal energy, of course, is heat. Mechanical energy is objects in motion. It's a little bit more than that, actually. Really, mechanical energy is a mixture of kinetic and potential, but we'll get into that another time, right? We don't have to worry about that today. Electrical energy, of course, is the one we've been talking about for weeks now. And then there's magnetic energy, which is actually very similar to electrical energy, but we won't really need to worry about that one right now either. Potential energies include chemical energy, which we've spoken about before, especially when we were talking about cells and batteries, because cells and batteries use chemical energy to produce electrical energy. Elastic energy, we haven't talked about that one at all. Nuclear energy, we haven't talked about that one either, but nuclear energy, of course, can be released and converted into electrical energy using nuclear power plants. We might get into that another day as well, but very interesting to understand. And then gravitational energy, basically just like, okay, you're holding something up and you drop it. Well, how does it move? Well, it's because there's gravitational energy provided to it by gravity from the Earth. Now, other energies that are a little harder to place into either one of these categories are sound energy and light energy. Personally, I think I would resoundingly put them in kinetic energy because they're both things moving. Sound, of course, is just vibrations in the air. Vibrations, of course, are kinetic. And light energy is electromagnetic radiation, which is kind of an interaction between electrical energy and magnetic energy. It's a really complicated thing. You'll learn about it if you ever take physics, but still I'd rather put that in kinetic energy, but they didn't for whatever reason. Whatever, doesn't really matter. Anyway, moving on. Oh, no, before we move on, let me just quickly remind you of the law of conservation of energy. The law of conservation of energy is a thing that says that energy cannot be created or destroyed. It can just merely be changed from one form to another. So energy isn't created out of thin air. You can't just say, oh, I'm going to make some energy. No, you're going to turn one form of energy into another form of energy. It does not get created or destroyed. It just gets passed around. Also, and this is a huge reminder here, the purpose of a load in terms of an electrical circuit, for instance, is to change energy from one form to another. The easiest example to think of here is a light bulb. And a light bulb is going to turn electrical energy into light energy as well as thermal energy. And all those energies I just mentioned are, of course, in this picture right here. So electrical energy is turned into light energy and thermal energy. Moving on. So chemical energy, I really want to break this one down because it seemed a while ago that we were kind of having a hard time understanding what chemical energy really is. Chemicals inherently store energy, right? So inside all chemicals, there's energy that's just stored in them. When chemicals react, they release that energy. Now, chemical energy is the entire reason why we use wood to make campfires. Wood contains chemical energy, and if you light it on fire, and remember, fire is just a form of chemical reaction, you're releasing that energy in the form of thermal energy and light, right? That's why wood is so useful to burn. You're not going to burn a rock, for instance. A rock doesn't have the proper kind of chemical energy, not to mention it doesn't burn, right? So at least not easily, right? So that's not going to work. Now, cells, which make up batteries, convert chemical energy into electrical energy. That was what's happening when you like cut a battery open. You're going to see there's a bunch of like paste in there, which is used to like induce a chemical reaction between that and some of the other chemicals that are in there to, of course, cause electrons to flow. You don't need to know it in terms of a very detailed process, but please just understand that a battery as a source of electrical energy is caused from a chemical reaction occurring within that battery. And it doesn't matter if it was a wet cell battery or a dry cell battery, it's still a chemical reaction that's occurring. Now, energy conversions. I want us to think of a bigger picture here, not just in terms of electricity. Remember from before, the conservation of energy says that energy cannot be created or destroyed, only merely change from one form to another. No matter what kind of energy you're looking at, no matter what you're looking at that has energy inherent with it, there's an energy conversion that must have occurred. So again, energy can undergo multiple conversions to become the form of energy that was desired. In battery-powered devices, so things that aren't directly hooked up to a wall outlet, for instance, in battery-powered devices, technically chemical energy is your input energy. It's what you're putting into it. You're putting a battery in your flashlight, for instance, and the battery contains a chemical. A chemical reaction occurs which releases electrical energy. So we have chemical energy first, then electrical energy, and then that electrical energy goes through to the bulb in the flashlight, which turns it into its useful form, or in other words, light energy, right? It would be the same thing with anything else that might use batteries. If you had, let's say, a battery-powered electric toothbrush, right? What that's doing is it's turning chemical energy in the battery into electrical energy inside the toothbrush, and then the bristles on the head of the toothbrush that are moving, that is a form of mechanical energy because it's a moving object, right? So again, it's just a bunch of energy conversions, and that's what we're doing here. Now, chemical energy, again, is the source of energy for animals. So even us, technically as animals, or any other living animal, needs chemical energy in order in order to convert it into other forms of energy, right? So our source of chemical energy, generally speaking, is glucose, right? Which is a form of sugar. So glucose is used to produce energy. So that's your chemical right there. Yes, sugar is a chemical, right? Technically speaking, it is a chemical, right? So glucose is your chemical. The chemical energy stored in the glucose is converted by your body into other forms of chemical energy. Actually, it's a thing called ATP. And then, of course, that is used as like a form of currency inside the cells of your body to allow yourself to perform mechanical energy. Your body actually also has electrical energy going through it. Your spine, for instance, carries nerve signals, and nerve signals, of course, are actually done through very, very, very small little electrical signals, which is kind of weird to think that we have like an electrical current going through us at some points, of course, right? But that is how we induce mechanical action. It is what really sparks our muscles, right? We also produce thermal energy. We give off body heat. That's produced from, of course, the initial source of chemical energy in the first place as well. So the food that you ate has been converted into other forms of energy for you to use. There you go. Of course, that picture that's been up here this whole time, you can take a look at that as well. It shows a bunch of different examples. We've talked before about a toaster example, of course. So the electrical energy from having that toaster plugged into the wall produces thermal energy, or in other words, heat, to cook your toast, right? That's the main idea. Oh, and I really like this one as well. Gasoline in your car, of course, that's a chemical. Your car is burning it, so it's causing a chemical reaction, right? It's happening inside your car. You're burning the gas, and then that combustion, of course, is what causes your car to be able to drive. There's mechanical energy. It's moving. Okay. Anyway, moving on. All right, this is the last thing we got to talk about today. I kind of told you it was going to be a quick day today. This is something that's kind of obscure, but you don't need to know it in great detail. It's going to maybe sound a little more complicated than it needs to be. It's called a thermocouple. So we've discussed a lot about things that use electrical energy, like toasters and lamps and stuff like that. But what about things that produce electrical energy? So in other words, there was some other form of energy that went in, and it's electricity that comes out. One of the strangest ones is something called a thermocouple. A thermocouple is a device that actually converts thermal energy, so heat is your input, and it turns it into electrical energy. You might be wondering, what on earth, why would you need something like that? Why would you be turning heat into electrical energy? Well, there's a few ways that this might actually be useful. But before we get there, let me just tell you that a thermocouple is made of two metals that are joined together, right? So there's a joint between two different metals. The metals are usually, of course, in the form of a wire. Now, each metal conducts heat at different rates than the other, right? So in other words, different metals are going to get hot or cold faster than other metals. They conduct heat differently. Now, the heat of a metal also affects its resistance, right? We're talking the electrical resistance. And when you have a change in electrical resistance, this can cause a change in your current and your voltage. So a very, very quick little interaction occurs where there's a sudden change in your whole Ohm's law characteristics, and that actually induces a voltage to be produced between these two different wires. So the temperature, of course, affects the amount of electricity that gets produced. So a huge shift of temperature, like if it was rapidly heated, for instance, that would cause quite a substantial change in voltage. relatively speaking, of course. We're really only talking about millivolts here, which are, of course, 1,000th of a volt. But still, that temperature can affect the amount of energy or electricity produced. So therefore, what I'm trying to ramble and get to here is a thermocouple can be used as like a really weird way of measuring temperature as a thermometer, right? So it can serve as a way of actually determining temperature. Now, thermocouples are used as thermometers in situations where a normal thermometer might be difficult to use. Two applications that came off the top of my head here were thermocouples inside of your computer. You might have already known this, but you might also not know this. Computers, as well as modern cell phones, actually have thermocouples that are built into their microcircuits. So right inside all the circuitry inside your computer or your phone are thermocouples, which kind of detect what the temperature would be at different times, right? So you can use different programs or apps. I know there's several apps you can get on your phone. On your computer, it's a little bit more complicated, but you can actually determine for different parts of your computer what the temperature would be, right? So in this screenshot that I just found on Google, this person has their computer, and of course there's different cores in their computer's processor, and each core actually had its own thermocouple, and it all has a different temperature reading. So you can see at different cores, there's different temperature readings, which is quite interesting. Now, there's not literal thermometers inside your computer measuring those temperatures at all those little points. These points could be very close together. Like these are just different cores inside your computer's processor, which is a chip that's really not all that big, right? So these aren't very far apart. A thermometer would be impossible to like stick in there and hold up against it and get a temperature reading. But with a thermocouple, it can be built right into the circuitry and spit out a temperature directly by measuring the amount of voltage that passes through it inherently on its own. Kind of creative. Kitchen thermometers, by the way, the one that has like a prod on it, you stick inside your food, oftentimes those are also made of a thermocouple. So inside that metal, there's two different types of metals. And of course, that can produce a change in electricity, which can produce a reading that can be read on the thermometer itself, right? It wouldn't be always ideal to literally stick like a thermometer, like with the liquid inside of it, inside your food. Not to mention you have to wait a while for that. Thermocouples can be used as a way around that. Anyway, I've rambled long enough about that. So here's some practice for you, page 323, questions 1 to 7. Give those questions a try. As always, make sure you're reaching out and asking me any questions if you're stuck. A lot of you guys just kind of sit in silence, and I don't hear back from you until I check in. And even with those check-in emails, make sure you're not just saying, okay, right? Like literally be like, yeah, I understand things. I'd really appreciate just to hear a little bit more feedback from you guys. Anyway, if you need any help, you know how to reach me. Best of luck.